Okay, so good afternoon to all. This is our seventh lecture session of the course Fluid Mechanics. So, in the previous lecture, we have discussed about different types of fluids, and then we started a discussion on new property which is called as surface tension of the fluid. And for surface tension, we have come up with two fundamental ideas. One idea is that it acts along the circumference or periphery of a free surface, and second important idea was that it can also be related in terms of amount of energy required to create a free surface. Okay, so that was the second idea. So typically, if you recall, what we have done, we did consider a rigid wireframe structure, and in this rigid wireframe structure we were having one movable wireframe over here, and with this movable wireframe actually we saw that if we suspend any soap film over here, then this, in order to maintain this rod at stationary position, we have to supply certain amount of force, and that force is nothing but equal to sigma surface times, if say B is the width of this rod, then a soap bubble will be having, a soap film surface will be having two interfaces, one at the top and one at the bottom. So that's why sigma s into 2b times. Okay. Another understanding in terms of the displacement of the rod, we have seen that surface tension coefficient can also be written as work done per unit area. Okay, dA. So here we have I have told you that surface tension coefficient is nothing but the amount of work done or amount of energy that we need to do in order to produce some surface incremental change in area of dA. Okay, so that is also called surface tension. And why we need to invest into energy in order to create a surface? Because molecule which is present at the core of the fluid, that is in its happy state, and when we are bringing it to the free surface, then actually it is coming in some unbalanced state or some tension, which is kind of unhappy state of the molecule. So when we are pulling it, then we have to do some work against the motion of the molecule. Okay, so that is something which we have studied in the previous lecture. Now we will extend this discussion. So in simple words, I can also say that, let's say if I have any liquid column, okay, so this is my liquid column, and this liquid column is having some surface area A. Okay, so now if I take some knife or anything, and then if I use it parallel to this surface, and if I split now this liquid column into two parts, so what will be happening? I will be having one top portion, okay, like this, and one I will be having one bottom portion. So if you see, earlier I was not having any free surface over here. So all the molecules were having nothing but the interaction with the like molecule. So cohesive nature of the interactions were there. Now when I have broken it and I have divided it into two surfaces, then I have got nothing but the formation of two new surfaces. So if A is area of each surface, say A is for this and A is for this, then ultimately I have got nothing but 2A amount of area. Okay, so this 2A amount of area, so whatever the energy I have to invest in order to create this cut, so that energy A will be, that energy or work W will be nothing but equal to sigma s times 2A. Okay, this point is clear. One important point, whenever I will be talking about the surface tension force, over this surface tension force will be acting always parallel to the surface. Okay, is this point clear? So surface tension force will be acting nothing but parallel to the surface over here. So how we can see this? Let me demonstrate this with the help of some more examples. So typically if you see, typically if you see what we have occurrence of, as I told you, we have occurrence of nothing but the bubbles as well as the drops. Okay, so in the surroundings of other fluid medium. Okay, so all these bubbles and drops, these are having spherical shape because of this surface tension. Okay, so surface tension from 2 points, we have come to know that either it can be written in terms of force per unit length. So when we are writing it force per unit length, then its unit is Newton per meter, and in second approach it can also be written in the form of amount of energy which we have invested per unit area, so that makes it joule per meter square. Okay, so these are the two different units of surface tension. So if we now consider a surface tension, it is not the property of a fluid, but it is the property of liquid and other surrounding fluid combination. Okay, how? For example, when we talk about surface tension, if I am referring to bulk of the fluid, at bulk of the fluid there will not be any occurrence of the surface tension. Where surface tension will come? Surface tension will come only at the boundaries where after the particular liquid I have nothing but presence of some another fluid medium. For example, over here I can say that if I take any molecule at the center, then around it everywhere it is having nothing but the equal interaction from all the sides. So here there is no role of surface tension. So surface tension is actually completely balanced. But on contrary, if I consider that here in the surroundings I have air, and if I consider any molecule over here, then in this region only I will be finding some unbalanced force. Okay. The reason is here I was having another type of molecule, and just adjacent to it there was some other type of molecule. Okay. So it means that surface tension is nothing but a binary property. It is not property of a single fluid medium. For example, if I talk about viscosity, then viscosity, if water is present, then I can simply say that at the core of the water as well as at the interface of the water also viscosity will be same, or it will be defined everywhere. Okay. But on contrary, surface tension will be defined only at the free surface when it is having molecules of some other fluid in its surrounding. So that's why it is property of a fluid pair. Okay, so whenever we define the surface tension, if I talk about water, then surface tension of water in the surroundings of air at room temperature is having magnitude of 0.07286 Newton per meter. Okay, but that is how I am defining it. I am defining it that surface tension of water present in air. Okay, so in the surroundings of air, if I consider same water, but in its surrounding, if I, in place of air, if I use any other fluid or any other liquid, then what will be happening? Value of surface tension will be changed. Okay, so now if I consider say water only in surroundings of pure oxygen or pure nitrogen, then I will not be having value exactly equal to 0.07286. In that case, I will be having some different value of the surface tension. So it means it is nothing but a binary property of the fluid pair which depends upon the liquid which we are considering and whatever the surrounding fluid is. Okay, is this one clear? Now, surface tension, of course, whenever say I am having surface in between, or I can say interface in between two immiscible liquids. So I may also have a situation that in a container I have say water filled inside it, and above that I have some oil present. So of course oil and water are of immiscible nature. So whenever two liquids are of immiscible nature, then we will be finding in between these two there will be some interfacial boundary which is called as interface. Okay. So any molecule which is present at this interface, that molecule will also be subjected to the tension. How? Because any water molecule present at the interface, that is having in the top direction, it has to interact with nothing but the surrounding oil molecules. Okay, and the interaction forces from the oil molecule to the another water molecule in the downward direction will be actually different. So here also I will be having some unbalanced force. So when we are having combination of say two immiscible liquids, corresponding to that, if we are having any interfacial boundary present, okay, then we call our surface tension as nothing but interfacial tension. Okay, so this is important point. So property of surface tension. So surface tension we refer whenever we are having any liquid, but its free surface is present in the surroundings of air. But if we have any liquid and its free surface is present in the surroundings of other liquid, then we will be calling that as nothing but the interfacial tension. Okay. So surface tension and interfacial tension, all these are nothing but the binary properties which depends upon the free surface and whatever the fluid is present in its surroundings. Okay. So as I told you, whenever I have talked about the surface tension of water and air, so this was 0.07286 newtons per meter at 20 degree Celsius. Whenever we increase the temperature, then upon increasing the temperature of the liquid, value of surface tension keep on decreasing. Okay, so this is another important point. If we have to study the dependence of surface tension with temperature, then upon increasing the temperature, the value of surface tension decreases. There is one situation when the temperature of the liquid becomes equal to its critical temperature, then surface tension of the fluid becomes zero. Okay, so if you are having any liquid and its temperature is becoming equal to that of the critical temperature, corresponding to that its surface tension will become nothing but equal to 0. Why at critical point surface tension becomes 0? Do you know what is critical point? Yes, temperature at which saturated liquid and saturated vapor meets, which is a multiple phases will be present in the two-phase design. Okay, so okay, let me show you once again. So if I consider phase diagram between temperature and specific volume, so what I will be finding, I will be finding a curve something like this. So this particular line is nothing but referred to as the saturated liquid line, and this particular line is referred to as saturated vapor line. So the meaning is, if you heat beyond this, then you will be having pure vapor, but in between this boundary you will be having mixture of liquid plus vapor. So where this saturated liquid and saturated vapor line meets, that particular point is called as critical point. Okay, and above the critical point, always we will be having nothing but gaseous phase present. There will not be any liquid. Okay, so above the critical point, what will be happening? Our liquid will get converted into gaseous phase. If liquid is getting converted into gaseous phase, then it will not create any free surface. If it is not creating any free surface, there will not be any surface tension. Is this one clear? We have seen in our initial lectures that under the category of fluids, there comes liquids and gases. Liquids are those fluids which creates free surface, but gases are those fluids which does not create the free surface. So any liquid, if its temperature is above than its critical point, it will be present completely in the gaseous phase. As it is present in the gaseous phase, it will not be creating any free surface. If it is not creating any free surface, then we will not be having any value of surface tension. Okay, because surface tension only acts at the free surface. So that's why at critical temperature, value of surface tension becomes 0, and if we keep on increasing the temperature, then its value decreases. Is this one clear? Now, Let's also try to see the surface tension of mercury. So if you talk about mercury, then it is having surface tension value of 0.44 Newton per meter. So you can see how high is the value. Okay. So that is the reason if you take a very smooth flat surface and over this flat surface if you place a water drop, it will be taking shape something like this. This will be the shape of water drop. But if you consider a mercury drop of equivalent volume, you will be finding it will be forming almost a perfect sphere and it will be rolling over the surface because its surface tension value is very high. Okay, is this point clear? So the point is, because mercury has very high value of surface tension, so it will be forming almost a perfect sphere. Its drop will be forming almost a perfect sphere. On contrary, if I have a water drop, that will not be able to form a perfect sphere because its surface tension value is low. Is this one clear? At the identical conditions. Okay. So this is something which is the very important implication of the surface tension. Now, there comes one important point. So we are always saying that whenever we are having the presence of free surface, we are having some sort of tension at the free surface. Okay. So of course, if a drop has to stay in spherical shape, or if a bubble has to stay in spherical shape, so whatever the tension is acting at the free surface, that tension has to be balanced by some forces. Okay. So typically that tension is balanced by nothing but the pressure forces. So basically the pressure present inside a drop is different in comparison to the pressure outside the drop. And whatever the difference of pressure is there, that is something which is balanced by the tension present at the surface. Okay. So let's try to understand this concept. So let's consider that I have a spherical drop of water. Okay, so I have a spherical drop of water of diameter d. So d is the diameter and this is nothing but a spherical drop of water. And if now I cut this drop from the center, so I have cut this drop like this. So in the surroundings I have nothing but air and this is liquid, some liquid drop I am having of diameter d. So if I cut this drop from the center, what will be happening? You will be finding that three-dimensional representation will be something like this. Consider this as the bottom part of the sphere. Okay, I have cut it like this. Now this is something which is nothing but the bottom part of the sphere. Okay, so now this is I have given a horizontal cut. Okay, so in this drop liquid, if you see what will be happening, let me rotate it through 90 degrees and plot it like this. Is this one clear? Now is it visible clearly? So what will be happening? This is the free surface. At this free surface everywhere I will be finding that surface tension force is actually acting. Okay? At the boundary, at periphery what we have? We have inside liquid, outside air. So at periphery we have the presence of the free surface. So at this free surface I will be finding that surface tension force is actually acting in which direction? In the tangential direction of the free surface. So basically this force acts perpendicular to the cut and parallel to the free surface. Okay, so whenever I have cut this, I have cut it like this, sliced it like this. So my plane of cut is normal. So if you see the direction of the surface tension force, it is normal to the plane of cut and parallel to the free surface. Okay, and let us consider that outside air is having pressure P naught. So here I can write that outside pressure is P naught and say pressure inside the drop is P. Okay, so P is the pressure which is inside the liquid drop. Okay, now there is this pressure difference of delta P. So delta P is nothing but equal to P minus P naught. So what will be happening? This outside pressure will try to create some uniform pressure field over here. Okay, and inside pressure will try to create some uniform pressure field, but its magnitude will be more. So this is some pressure is acting from inside. So if I see as a whole from inside to outside, my drop surface is subjected to some pressure delta P. Is this point clear? Any doubt up to this point? So now if you see, say D is diameter of the drop, what will be its circumference? What will be the circumference of the drop? Circumference of the drop will be pi into D. Pi D and sigma S is my say surface tension coefficient. So pi D into sigma S is nothing but the surface tension force acting over here. So this is the surface tension force which is acting on the drop. Okay. Now if you see, this is surface tension force, but there is some pressure force also. And if you see the direction of these arrows of pressure, this is nothing but opposite to direction of the surface tension force. Okay, so it means that whatever the force we can quantify because of the pressure, that is being balanced by the surface tension force over here. Okay, so if you see, so this pressure is acting on this complete periphery of the surface, but we are now trying to find the forces only in the horizontal direction. Okay, because we have taken this slice in such a way that only the horizontal component of the surface tension is coming into this picture. Okay, so if I have to consider only the horizontal contribution of the pressure force, then can you tell me what will be the projected area of this sphere in this direction? So in this direction, if you see, so projected area of sphere is nothing but pi by 4 d square. Okay, so pi by 4 d square is the projected area of sphere in this direction. Okay, so ultimately on this projected area pressure is acting. Okay, so pressure force over here is how much? That is delta P into pi d square by 4. Okay, and ultimately this pressure force and this surface tension force, these are actually being balanced. Okay, so I can write then delta P into pi by 4 d square is equal to pi d into sigma s. So pi will cancel out, and 1d will also cancel out. So from here I can say that delta P is nothing but equal to 4 sigma s by d. Okay, so one important point from here we can say is that pressure on the interior portion is, interior of the drop is greater in comparison to pressure on the outside. So if you see, the interior surface of the drop is nothing but making a concave shape. So this is nothing but a concave shape. So we can say that pressure always on the concave side of the interface is greater than the convex side. Is this one clear? So this free surface is having concave side towards inside of the drop. So we can say from this point, because this delta P will be positive. Okay, surface tension sigma s is positive over here, diameter is also a positive quantity, and we have already considered that delta P as nothing but P minus PO. So as delta P is coming positive, it means P is greater than PO. So in this situation, I can say that pressure on concave side will be greater than the pressure on other side. Okay. Okay. Is this one clear? So basically, whatever the tension is acting at the free surface, that tension is balanced by the pressure force. Inside the drop, pressure will be more. And if you see, this pressure difference is nothing but inversely proportional to diameter. So it means that small sized drops will be having more pressure in comparison to the large sized drops. So if you have a bigger drop, then its inside pressure will be less. Okay. Now, whatever the formula we have derived from the drop, same will be applicable for a bubble if it is present in a surrounding liquid medium. Okay. So if I consider, say, that I have water filled inside some container, okay, and inside this container I have the presence of a spherical air bubble. If I have spherical air bubble of diameter d over here, then you will be finding that here we are having only a single solid liquid interface. So sorry, liquid gas interface. So as we are having single interface, so here also the interfacial forces and the pressure forces will be identical to that of the drop case. So for this type of situation, for air bubble present in another liquid medium also, I will be having delta P as nothing but 4 sigma S by D. So this is for air bubble, or I can even say gas bubble present in liquid medium. Fine. Now if you consider another situation, if in place of the air bubble you say that you are having nothing but a soap bubble, then what will be happening? Yes, if you have a soap bubble, then you will be having this type of situation. This is the liquid interface of the soap bubble, okay, thin liquid film of the soap bubble. Inside this you have air, outside this also you have air. Okay, so now the situation is, if you see, then you have this situation: inside air, then a very thin liquid film. This is a very thin liquid film, and then outside also air. So here how many interfaces you have now? One is this interface and another one is this interface. So it means surface tension is acting at two interfaces. So if it is acting at two interfaces, so in the previous force balance, when we have calculated the surface tension force, in place of pi d into sigma s, it will be nothing but 2 pi d into sigma s, considering the liquid film thickness is negligible. So whatever is the diameter of the inside of the bubble, same is the diameter of the outside of the bubble. Okay, so considering that, I will be having how many interfaces? 2. So that's why whenever I will be writing delta P, that will be becoming 8 sigma S by D. Is this point clear? Or anyone is having any doubt on it? Up to this, is it clear? Now let's consider the third situation. Third situation is, say I have a cylindrical liquid element. Okay, so if I have a cylindrical liquid element, say a cylindrical rod of liquid, so say I am slicing it from this section plane. If I am slicing it like this, then what I will be getting? Okay, so this will be my cylindrical portion. Now, perpendicular to the cut, we have surface tension force. So surface tension force is acting like this. Say D is its diameter and L is length. then this dimension from here to here is L and this is D. So now can you tell me what will be the magnitude of surface tension force? Sigma S into LD. Where surface tension force is acting? Is it acting on area or is it acting on interface perimeter? 2 times L plus D. Okay. So because surface tension force is only acting at the interface. Okay. So perimeter of this will be like this is L, this is D. So L plus D is 1 and then 2 times of L plus D. So that is the surface tension force. And this force now has to be balanced with which force? Pressure force. So let's consider outside pressure is P naught, inside pressure is Pi. So pressure difference is delta P, and where this pressure is acting, this is acting on projected area. So what is the projected area if we see from the top? Projected area is rectangle L into D. So delta P into L into D. Okay. So from here you can see that delta P is nothing but equal to 2 times sigma S, and now divide by L and D. What you will be getting? 2 times sigma S into 1 by D plus 1 by L. Now if you take the assumption that D is very very small in comparison to L, in that case 1 by L will be very very small in comparison to 1 by D, and you can simply write that delta P is equal to 2 sigma S by D. Is this one clear? Considering the assumption that our L is very large. Okay?
If we consider vertical plane, then relation to become equal.
Sorry?
Will the relation become equal?
If we consider a
Vertical plane.
yes, then D and L, then also it will be same.
But basically will be acting on the circle.
Okay, you are saying plane like this. Okay, yeah. So presently, if you take vertical also in this plane, then it will be same. But if you take plane like this, then it will be different. Yeah. So if you take plane like this, then actually it will be a different situation. But corresponding to that, then we are not having any pressure difference in this direction. Okay.
D and L will be related.
Sorry.
Then D and L will be related.
D and
L will become related.
yes. Then DL will be related. Okay. Is this one clear? So basically, two-dimensional liquid column is very very difficult situation to exist. So if you see a long cylindrical column, so that is very rare case that you will be finding it is actually forming. So if you are having too much inertia dominant situation, then only it will be forming. Otherwise, it will be breaking into the it will be breaking into small droplets. Okay. Okay, up to this point, is it clear? Now, whatever the concept I have explained in terms of the forces, same concept can also be explained by considering the energy concept. Okay, how? You can consider that initially you are having, say, drop of radius r, okay, and say because of the now what you have done, you have subjected it to some force so that it is elongating through some radius dr. Okay, so if it is elongating through some radius dr, then what will be the work due to surface tension? We know that work due to surface tension is nothing but sigma s into increase in area. So increase in area is dA. Okay, so sigma s into d of area of this one is 4 pi r square. Okay, so that is the work because of the increase in incremental area dA. Okay, now what will be the work because of the pressure? Work because of pressure can also be written as delta P into 4 pi r square will be the force. This will be the force. Okay, 4 pi r square is the area at which this force is acting. So delta P into 4 pi r square is force into displacement. So displacement is how much? dr. Because in complete bubble it is completely expanding. Okay, so each and every part of the bubble is actually going through displacement dr. Okay, so force at each and every point was nothing but delta P into 4 pi r square, and displacement is dr over here. So in this situation, now if we equate equation number 1 and 2, then I will be finding that sigma s into 4 pi is constant, d of r square will become 2r into dr, that will be equal to delta P into 4 pi r square. So if you see 4 pi is cancelling out, dr is also cancelling out, 1r is also getting cancelling out. So from here you will be finding delta P is equal to sigma s by r, or it can be 2 sigma s by d. So whatever earlier we have calculated. Fine. Anyone is having any issue with this concept of work? If there is any doubt, you can ask me. Okay, up to this point, is it clear? Is it clear? Now, another way of calculating the pressure drop at a curved surface is that you can calculate actually the,
So that is 2 sigma s by r.
that is 2 sigma s by r. Okay, yeah. So 2 sigma s by r, and it will be 4 sigma s by r. Yeah, so if you see earlier also, the relation you have calculated, that is 4 sigma s by. So means either by using the force balance or by using the energy balance, actually we can calculate. Okay, but whenever we are having the complex interfaces present, where we are not having any symmetry available, then we have to go for another method of calculation of the curvature in order to define delta P. Okay, so how we can do that? Let us consider that I have some curved surface like this, and on this curved surface, say I have some small elemental area. Okay, now if I elongate this elemental area, say this elemental area is looking something like this. Okay, so what will be happening, say in this direction, if I fit a circle over here, it is having some radius r2, and in this direction if I fit a circle, then it is having some radius r. Okay, and let us consider this angle is d theta 1 and this angle is d theta 2. So if I am having any arbitrary shape of a curve, so if I have a sphere, and at the surface of the sphere if I take any small element of area, then in both the perpendicular planes it will be having same radius of curvature. But if I am having any arbitrary shape of the curve, okay, for any arbitrary shape of the curve, what I will be having? I will be having in two perpendicular planes, I will be having different value of radius of curvature. Okay, so say one radius of curvature is r2 and another radius of curvature is r1, and angles are d theta 1 and d theta 2. Okay, so over here what will be happening? Here also there will be some surface tension force parallel to the interface, and here also there will be some surface tension force parallel to the interface. So this complete interface is subjected to nothing but the tension. Then only it is formed. So in the tangential direction, it is subjected to some surface tension sigma s. And inside this surface pressure is P and outside this surface pressure is P naught. Okay. Is this point clear? Up to this point, is it clear? Now if I have to quantify the magnitude of these forces, then what will be happening? I have one curvature like this, whose angle is d theta 1 and radius is r1. Okay, and at this curvature, if I see the magnitude of the surface tension force, that is how much? This is the sigma s, and for this plane, if r2 is radius, then this circumference will be how much? r2 into d theta. So I can say that the magnitude of this surface tension force is nothing but sigma s and r2 into d theta 2. Fine. Is this point clear? And if this angle is d theta 1, then whatever the angle made by this surface tension force over here, how much will be this angle? Can you tell me what will be this angle? D theta 1 by 2. Clear? This point is clear? Similarly, I can take the other plane. If I take other plane, that will be r2 and this will be d theta 2. What will be the magnitude of forces now? Now the magnitude of forces will be on this line. Okay, so on this line, force will be sigma s into r1 d theta 1. Is this point clear? And what will be angle now? D theta 2 by 2. Okay. So now if you see, these are the surfaces. Pressure, inside pressure is P, outside pressure is P naught. So pressure force is acting in which direction? Vertical direction, means in all the directions, but say if we take the force balance along the vertical direction, then along the vertical direction, how much is surface tension force? Sigma s r d theta 2 and sigma s r d theta 2 is coming from here. So 2 sigma s into r2 d theta 2, and it will be having some component. In vertical direction, the component is sine of d theta 1 by 2. Similarly, from here also this force is coming. So from here force is how much? Plus 2 sigma s into r1 d theta 1 into sine of d theta 2 by 2. So this is the total surface tension force. Now this total surface tension force must be equal to the pressure force acting in vertical direction. So pressure force is how much? Delta P into area. What is area? If you see the area of this surface, that is nothing but r d theta 1 is this side, r2 d theta 2 is this side. So area of the surface will be r1 d theta 1 into r2 d theta 2. Is this point clear? So r1 r2 d theta 1 d theta 2. These are the areas. Okay. So considering the fact that d theta 1 and d theta 2 are very small, Sin d theta 1 and sin d theta 2 will be nearly equal to d theta 1 and d theta 2. Okay, so from here I will be finding that d theta 1 and d theta 2 will be cancelling out on the both sides. So if I calculate delta p, that will be becoming 2 times sigma s 1 by r1 plus 1 by r2. This is one very important equation which is called as Laplace equation. So if I have any free surface present and if you want to find out the pressure difference across the free surface, then I can simply find out by using this relation that 2 sigma s times 1 by r1 plus 1 by r2, where r1 and r2 are nothing but the radius of curvatures in two principal planes. Okay, so sum of 1 by r1 plus 1 by r2 will be becoming nothing but the curvature of the free surface. Okay, so this whole quantity we call as nothing but the curvature of the free surface. So if we multiply surface tension force with curvature of the free surface, in that situation we will be finding nothing but the pressure difference. So this is the very famous equation which is called as Laplace equation. Now if you want to apply this equation for a sphere, how you can apply? Say this is your spherical shape. If you take any control volume or any small surface over here over this sphere, okay, so what will be the principal directions? First you have to take normal to this surface, then you have to take two perpendicular planes such that these are intersecting at the normal, and now if you are fitting any circle which is tangent to this surface at the principal planes, these will be becoming nothing but your principal directions. Okay, and for a sphere, because sphere is a symmetric shape, for sphere the value of these two principal radius of curvatures r1 will also be equal to r will be equal to r2. R1 and R2 will be same. Okay, so if you have a sphere, and for sphere if you take two principal perpendicular planes, in each of the plane if you fit a circle which is tangent to the surface of the sphere, both the circles will be nothing but having the same radius. So R1 and R2 will be the same. So that is why if you see delta P will be becoming from this point 1 by R and 1 by R will be becoming 2 by R. So 2 by R makes it 4 sigma S by R. Is it correct? It should be 2 sigma S by R. Oh, sorry. I have missed. Yes, this is the mistake which I have done over here. So if you see, when we will be approximating this d theta 1, so sine of d theta 1 by 2 was there and d theta 2 by 2 was there. So this 2 will cancel out this particular 2 value from here. So this 2 will not be here. Okay. So now if you do, then it will be coming as 2 sigma S by R, which is nothing but 4 sigma S by D for a sphere. So this is for a sphere. Please make this correction. So whenever I have taken the approximation of the angle, I have not deducted this 2 which is present in the denominator. Okay? Is this point clear? So it means that this Laplace equation, sigma s times of the curvature of the free surface, this is nothing but a generic equation, and this generic equation we can apply to any situation. Okay, this generic equation I can apply to any situation. If I apply this generic equation, I have to just measure at that particular point where we want to calculate the surface tension force, we have to measure the curvature. Okay, and curvature can be measured by first drawing a normal to the surface, and then considering two perpendicular planes which are intersecting at that normal, and whatever the radius of curvature, which is radius of a circle which is tangent to that particular curve, we will be getting that radius defined nothing but the radius 1 by radius of that circle is nothing but radius of curvature in that plane, and if we take sum of these two, that is called as mean curvature of the surface. Okay, so one important point, say I have a small bubble over here and it is connected to some another big bubble. This is connected through some tube. Can you tell me what will be happening over here? This is one large bubble and this is one small bubble. So what will be happening over here? Both are in the same surrounding medium, P naught, and these are connected through a tube. What will be happening over here? Small bubble will collapse. So what will be happening over here? If you see, the curvature of the small bubble is actually large because its radius is small, so curvature is large. So it will be having more. If this is P1 pressure, this is P2 pressure. So pressure at P1 will be greater in comparison to pressure at P2. So that's why in this situation what we will be finding? We will be finding that fluid will flow from small bubble to the bigger bubble. Okay, so size of bigger bubble will keep on increasing till the point this entire complete small bubble is actually diminishing. Okay, now let me give you one problem. So this you have to try. Let us consider that we have one bubble of d1 diameter and m1 mass, and another bubble of d2 diameter and m2 mass, and these two have joined together to form third bubble having size d3 and mass m3. And let us consider this process of coalescence has taken place at the isothermal conditions. Means their initial temperatures and final temperatures all are remaining the same, and let us consider their temperatures are also the same. So every bubble is at temperature T. Okay, and this coalescence is happening in such a way there is no mass loss. It means mass of the final bubble is nothing but mass of first bubble plus mass of the second bubble. What you have to do, you have to derive the relationship in between pressures and diameters of the two bubbles. So ultimately you have to find out pressure of the third bubble as the function of pressure of first bubble and pressure of the second bubble. Okay, and consider that the fluid present in all the bubbles obeys the ideal gas equation, P is equal to rho RT, and all the fluids are having, all the bubbles are having the same fluid, same gas present. Okay, so you have to determine the relation for P3 as function of P1 and P2. Is this point clear? So this is one question problem to you, and also I suggest all of you please go through your books. In the books there will be lot of numerical problems. Start solving the numerical problems. Probably in the next lecture I will discuss one or two questions in the class as well. Okay, and then after the second module is over, then I will give you one detailed assignment based on first and second module. Okay, but also try solving problems by your own as well.